Hi, I'm Elom, and in this video, we'll be dealing with a transfer function by finding the pole, zeros, and stability.
Hi, my name is Xavier, and this is a transfer function G. So first of all, solve for the zeros, and then the zeros are the roots of the numerator of the transfer function, and then the numerator of the transfer function is s squared plus 4s plus 3. So to solve for the roots and the zeros of this, we solve it quadratically to get the factors s plus 1 and then s plus 3. So after solving this, it equates to 0. Then we get the zeros to be s equals -1 and s equals -3.
Solving for the poles of the transfer function, which is the roots of the denominator of the transfer function. So we factorize s from the denominator to get this expression. Then upon further factorization, we get s bracket open s squared plus 3s plus 4 and s squared plus 4s plus 2 all equal to 0.
My name is Eugene, and after finding the factors of the denominator, we would equate each of them to 0. And so for our first factor, s being equal to 0, our first pole becomes 0. We take our second factor, s squared plus 3s plus 4, equating it to 0. We get our roots, -3 plus or minus root of 7i, all divided by 2. And breaking it down into decimals, you have our s1 being -1 plus 1.32i, and our s2 being -1 minus 1.32i. And then we take our third factor, s squared plus 4s plus 2, and equate it to 0 again. So same concept, we get our factors to be -2 plus or minus root of 2. And in decimal form, we get -0.5858 to 4 decimal places. And then same for the last factor, -3.4142 to another 4 decimal places.
For the system to be fully stable, all poles should have negative real parts, but we have one pole at the origin, which makes the system marginally stable.
So based on the transfer function we were given, we were able to determine the zeros. That was based on the root of the numerators, the poles based on the root of the denominators, as you can find here. And then we were able to determine that the system is marginally stable because it had one root equating to 0, which was on the vertical line, making the whole system marginally stable.